Hello everyone, my name is Neil Trevett. I am Vice President of Developer Ecosystems at NVIDIA, and I'm going to be speaking today as President of the Khronos Group and giving an overview of Khronos standards for embedded compute and vision acceleration. If you haven't met us before, Khronos is an international, non-profit standards consortium that is open to all, and our standards are royalty-free for the industry to use. Our focus is on enabling applications to access the power of acceleration for 3D graphics, virtual and augmented reality, vision processing, and parallel computation. We were founded in 2000 and we have close to 200 members from all around the world. So why do we need parallel processing? The simplest way to program an application is to code it to run on a single CPU. However, as Moore's law slows and processors are no longer running at faster and faster frequencies, the only way to gain more performance for demanding applications is to use multiple processors. Often a multiprocessor system contains a single CPU with one or more offload processors that often have specialized acceleration architectures, such as GPUs, DSPs, or specialized domain-specific hardware. Programming such parallel processing systems is significantly more complex than programming a single processor. Work has to be divided and distributed across available processors. Multiple processors have to synchronize and communicate their results. Proven and widely deployed parallel processing open standards that have been designed with the collective expertise of multiple companies over many years can greatly simplify the design and programming of these complex parallel systems. So how do open standards enable proven technologies to be pervasive? What is their superpower? The answer is that an open interoperability standard is a shared specification, together with rigorous conformance tests that define precise communication, in this case between hardware and software. This enables reliable implementations to be built and shipped by multiple companies to meet the needs of diverse markets, price points, and use cases, enabling that technology to be used pervasively across the industry. Open standards are often used for hardware APIs as they enable diverse competing hardware implementations. By contrast, open source projects enable multiple contributors to cooperate and share the work in building a single shared implementation, and are often used to implement software, libraries, and languages where a single consistent implementation is an advantage. Both open source and open standards are powerful tools, and open source projects are often used to enable open standard ecosystems, but the two are often confused. It's important to understand the different strengths of open standards and open source to be able to select the right tool for the job at hand. The tech industry uses thousands of hardware and software interoperability standards. They are essential to remove industry friction and to grow market opportunities for everyone. Well-designed open standards precisely define interoperability, but do not overprescribe implementation details, and so they unleash the power of innovation and healthy competition between different implementations. Effective standardization does not mean a race to the lowest common denominator. Successful open standards are created when a technology is well understood and the need for cross-vendor consistency is recognized by all. Truly open standards are not controlled by a single company, and so standards organizations like Khronos enable multiple companies to work together to develop a consensus on standards that benefit the entire industry. Effective standards organizations have well-defined governance and intellectual property frameworks and typically have a specialized area of expertise. In general, the more inclusive the organization, the better the chance that a standard will be widely adopted. Standards can provide significant value in embedded systems by decoupling software and hardware design for easier development and integration of new components, cross-generation reusability, and field upgradability. Effective standards reduce costs, shorten time to market, and lower the barriers to using advanced techniques such as parallel processing for faster inferencing and vision processing. And often they enable industry-wide shared development of an ecosystem of tools and libraries. So how is Khronos organized as a standards organization? Khronos hosts multiple working groups with a separate working group for each Khronos standard. Any company or academic organization is welcome to join Khronos and participate in any working groups that are of interest. Each working group produces the specification that defines its own open standard, together with conformance tests, tools, documentation, and educational materials. All these work products are made freely and openly available to the industry. Implementers of Khronos standards that wish to come under the protection of the royalty-free patent license made possible by the Khronos IP framework can join the Khronos Adopters Program for a small program fee, submit their conformance test results, and become officially conformant. There is never any per-device royalty to ship Khronos standards or any costs for developers and users of Khronos standards. Here are the standards currently being most actively developed by Khronos. There are 3D acceleration APIs, including Vulkan and OpenGL, and the new higher-level Inari API for driving rendering engines. Initiatives around 3D asset formats include GLTF for 3D assets and KTX for GPU textures. The OpenXR API standard for portable augmented and virtual reality, and on the right, a family of APIs and languages for parallel computation, vision acceleration, and inferencing, including the new Cameros camera API. We also have safety-critical versions of OpenGL, Vulkan, and SYCL for use in systems that need to be safety certified. Khronos develops multiple standards for parallel compute acceleration, providing a choice of APIs that are suited to different markets and developer needs. The APIs on the bottom row of this slide provide low-level, explicit control over accelerator hardware. Vulkan is used for programming GPUs, and OpenCL enables software to use any mix of available heterogeneous processors. Both OpenCL and Vulkan provide parallel acceleration of shaders or small kernel programs compiled to Khronos' SPIR-V intermediate language. SYCL and OpenVX on the top row of the slide are higher-level programming frameworks for increased application portability across diverse processor architectures. SYCL provides parallel programming using standard C++, and OpenVX uses a graph abstraction to express vision and inferencing functionality and can directly import trained neural networks in the Khronos NNEF format. SYCL and OpenVX may be accelerated by the lower-level Khronos APIs, but that is a choice left to the implementer. Third-party libraries for imaging, vision, video, and inferencing processing often use lower-level Khronos APIs, such as Vulkan and OpenCL, for access to hardware acceleration. To look at OpenCL in a little more detail, it is a low-level standard for cross-platform parallel programming of diverse, heterogeneous processors found in supercomputers, servers, PC, mobile devices, and embedded platforms. OpenCL is a runtime and programming framework that includes C and C++ based languages for creating compute-intensive kernels that can be compiled and executed across any available parallel processors in a system. OpenCL provides APIs to discover accelerator devices, compile kernels for selected devices, execute those kernels with explicit control over kernel placement, memory allocation and synchronization, and finally gather the results. When deciding between OpenCL or GPU APIs such as Vulkan, many developers find that OpenCL provides a simpler programming model, a lighter weight runtime, more language flexibility compared to graphic shading languages. For example, OpenCLC has pointers, and more rigorously defined numerical precision for math operations that can be critical for many applications. However, many developers, particularly those developing machine learning applications, often don't use such low-level APIs such as OpenCL or Vulkan, but rather use high-level frameworks such as TensorFlow or PyTorch. However, any machine learning framework will need to access a low-level API for accelerated performance. This is typically achieved through a machine learning library or compiler that converts trained networks in a high-level framework to low-level API commands. As this slide shows, machine learning frameworks use a variety of back-end proprietary and open standard APIs. The OpenCL and Vulkan open standards are widely used to support machine learning stacks, and they enable machine learning compiler and library vendors to reduce the number of proprietary backends they must support. The support for open standard backends is also interesting for hardware vendors developing inferencing accelerators. Supporting an open standard on an accelerator can bring immediately compatibility with many key machine learning frameworks and compilers, significantly accelerating an accelerator's time to market. OpenCL is being increasingly widely adopted by diverse hardware vendors and is continuously evolving with regular specification updates and an active roadmap including upcoming extensions for functionalities such as recordable command buffers, unified shared memory, cooperative matrix, and other machine learning primitives. There are also multiple open source implementations that are bringing OpenCL to a widening range of platforms. Many operating systems, such as Android for example, include Vulkan as part of their platform definition to provide access to GPU acceleration, and there is increasing interest in layering OpenCL over Vulkan to provide a convenient, easy-to-use parallel computation programming layer. Now to look at SYCL. SYCL is a C++ language framework that uses template libraries to dispatch selected parts of standard C++ applications to acceleration processors. SYCL enables complex C++-based applications and libraries such as complete machine learning frameworks to be directly compiled and accelerated to performance levels that in many cases outperform hand-tuned code. Offloaded C++ code is sent to the SYCL compiler for the targeted accelerated processors, often using OpenCL as a backend, but SYCL is increasingly supporting a wide variety of backends for deployment flexibility. The unaccelerated remainder of the C++ code is sent to the standard C++ compiler for the host CPU. The latest version of SYCL, SYCL 2020, uses unmodified C++17 for single-source programming with acceleration offload. One of the long-term goals of SYCL is to influence the ISO C++ roadmap so that one day C++ itself will be able to support heterogeneous computing. Realistically, though, this may take some time, and in the meantime, SYCL provides a standardized way to use standard C++ to achieve acceleration offload to OpenCL or other low-level APIs. SYCL is gaining industry adoption in desktop, embedded, and HPC markets. For example, the DPC++ language, which forms a key part of Intel's One API initiative, is a conformant implementation of SYCL and supports CPU, CUDA, and ROCm backends. In addition to OpenCL, Heidelberg University's adaptive C++ SYCL implementation also supports multiple backends, including OpenCL, AMD's ROCm, Intel's Level 0, NVIDIA's CUDA, and OpenMP for utilizing multiple CPUs. The SYCL working group is also working to upstream SYCL support into the LLVM compiler infrastructure. In addition to production versions of SYCL, there are multiple experimental implementations, including Tricycle from AMD, Baixing C++ from Huawei, PIMS from Samsung, and NeoCycle from Tohoku University for the Essex Aurora Tsubasa Vector Accelerator from NEC used in HPC systems. Such a wide diversity of experimental systems should enable SYCL to evolve rapidly to meet emerging market requirements. The SYCL roadmap is looking forward to SYCL Next, that takes the widely adopted portions of SYCL 2020, plus proven SYCL extensions, plus new functionality that includes improving performance and functionality of queues, task graphs, and hierarchical parallelism. The SYCL working group is seeking industry feedback and roadmap requests on the SYCL forums or the SYCL specification repo. The links are here on the slide. To encourage the development of an open-sourced accelerated computing ecosystem, including Intel's OneAPI DPC++ compiler based on the SYCL specification, the new UXL Foundation has recently been formed at the Linux Foundation. Khronos and UXL will work closely to align their complementary efforts and have recently executed a liaison agreement to ensure effective collaboration between the two organizations. The second Khronos high-level vision and compute API is OpenVX, which uses a graph programming model. OpenVX graphs enable a developer to program complex vision algorithms by simply connecting a set of predefined functions or nodes. OpenVX enables inferencing acceleration alongside classic vision functionality, and is increasingly being used as a portable inferencing engine. OpenVX accelerates inferencing by defining nodes to represent neural network layers, and a set of tensor and tensor operations to represent classes of neural networks typically used in edge inferencing. OpenVX can import a complete trained network in the Khronos NNEF Neural Network Exchange format, imported from machine learning frameworks using Khronos open source tools. NNEF's unique value in the industry is that it provides a stable specification to be directly imported by hardware drivers. The OpenVX roadmap is evolving to meet market needs. OpenVX versions 1.0 through 1.3 were focused on broadening the range of node functionality to be used within an OpenVX graph. The number of nodes grew significantly, and so OpenVX 1.3 introduced feature sets that grouped nodes into domains to reduce fragmentation. Now OpenVX 2.0 is under development, and many implementers are developing custom nodes, especially using ML frameworks. And so the focus has shifted to the graph framework that enables flexible pipeline data flow through target hardware with seamless custom kernel support. OpenVX 2.0 will define OpenVX Core, and this will provide this key graph framework functionality and will enable flexible mixing of custom and any OpenVX nodes needed to meet customer requirements. Increasingly, Khronos APIs are being used in a wide range of markets where reliable deterministic graphics and compute acceleration is essential, including the automotive market where formal safety certification is required to meet international standards such as ISO 26262. Khronos is evolving a set of safety-critical APIs that reduce system-level certification costs by creating streamlined versions of widely adopted desktop APIs. The safety-critical versions of these APIs focus on the needs of embedded markets and provide rigorously defined deterministic behavior to simplify system design and testing. Khronos' experience with safety-critical APIs goes back to 2003 with OpenGL SC 1.0 for avionics displays and OpenGL SC 2.0 in 2016 for the automotive market. and in March 2022, Khronos released Vulkan Safety Critical 1.0. Desktop Vulkan is a compelling starting point for creating a new generation safety critical standard, as it has reduced driver complexity compared to OpenGL, and Vulkan SC further reduces driver size while strengthening API determinism and error handling. OpenGL and Vulkan, though, are not the only Khronos safety critical APIs. OpenVX has a safety critical profile for offline compilation of OpenVX graphs into vendor-specific binaries for direct import into the runtime, significantly reducing API complexity. The safety critical profile is generating significant interest in OpenVX as a cross-platform inferencing engine for safety certified systems. And most recently, a SYCL SC working group has been formed to develop a safety critical version of the SYCL standard. Now let's talk about camera system APIs for embedded vision. The embedded vision industry has experienced rapid growth, with millions of cameras being deployed in drones, robots, smart devices, and autonomous machines and vehicles, along with AI to make sense of visual data. However, historically, camera vendors have exposed sensor functionality through proprietary APIs. This creates a significant burden on software developers and system integrators when switching or upgrading camera systems. The industry's need to fill this gap in the open standards landscape is becoming more urgent as cameras are becoming deployed in a growing number of increasingly complex systems, often with multiple cameras of different types, needing close integration with downstream processing that demands precise control over the generation of the stream of images from the sensor and ISP. This situation is driving the need for an open standard API to accelerate innovation and to reduce costs. In response to this growing industry need, the Cameros working group at Khronos has been formed to develop an open, royalty-free standard for controlling camera system runtimes in embedded, mobile, industrial, XR, automotive, and scientific markets. The new Cameros API standard will provide portable access to cameras, sensors, and ISP acceleration to ease integration of new sensors, enable reuse of application code across generations of camera and sensor hardware, while providing sophisticated control over sensor stream generation. Cameros will provide a carefully designed API that abstracts implementation details of the underlying camera hardware while enabling software developers to fully utilize the camera's capabilities with no need to disclose proprietary sensor and processing pipeline details. In return, by implementing the Cameros API, hardware vendors will become compatible with a large ecosystem of libraries and applications. Cameros is an application-facing user space API. It has been designed to be deployed on diverse operating systems and underlying hardware architectures and used by applications, frameworks, and libraries. Cameros will be callable through multiple language bindings, including C, C++, and Python. Cameros is also expected to use explicit low-level Vulkan-style resource management, synchronization, and command queues, with a focus on minimalization and efficiency to meet the highly sensitive latency and throughput requirements of embedded vision workloads. Open-source layered helper libraries can be used to simplify programming for common use cases. Although Cameros is still in design, the API will likely keep exact compatibility with Vulkan to enable a standalone camera API reusing base Vulkan functionality, or enabling Cameros to be deployed as an actual Vulkan extension, so that a single Vulkan runtime can support camera, streaming, compute, and graphics capability, greatly simplifying software, for example, for SoC vendors shipping in XR systems. As well as saving design time and reducing design risk, reusing proven Vulkan designs also enables use of the Vulkan command dispatch system with loadable layers for validation, profiling, and debugging. The Cameros API will enable programming of the camera and sensor hardware and ISP processing, including 3A, image statistics, and frame metadata. As with any Khronos API, Cameros will not dictate implementation details, enabling use of, for example, CSI2 or USB cameras, and a wide range of ISP architectures, including dedicated hardware, DSPs, or GPUs. Cameros does not define downstream vision, inferencing, or other compute processing that is left to existing APIs, such as OpenCL or OpenVX. Camera functionality could easily be integrated, for example, into an OpenVX node for feeding an ISP process sensor stream into an OpenVX graph. Cameros is an abstracted API that frees developers from writing code tied to specific hardware details, so that Cameros applications can be used portably across different devices. Cameros will enable applications to identify and select available cameras in a system, discover camera properties and whether they meet the needs of the application's use cases. The application can then discover, configure processing pipelines and settings via pipeline templates that make full use of hardware capabilities, including multiple inputs and output streams. Pipeline templates enable Cameros to address the needs of a broad spectrum of camera developers and vendors. Simple templates configured for common use cases will be widely supported, enabling broad portability for applications that wish to start acquiring frames after just a few API calls. Developers who wish to use camera capabilities can use the Cameros API to precisely configure processing pipelines to suit their needs. Camera vendors can also publish sophisticated pipeline templates to expose advanced or custom pipelines that have been tested and tuned for efficiency. Once sensors and processing pipelines are configured, Cameros enables frames to be requested using per-frame dynamic controls, with all applied settings and any exceptions returned in per-frame metadata. The European Machine Vision Association, EMVA, and Khronos cooperated to establish the Cameros working group at Khronos and have created an advisory panel through a liaison agreement between the organizations, which any member of EMVA can join at no charge. The Cameros working group will soon have draft specifications to distribute to the advisory panel for discussion to get feedback and input from the EMVA community. So thank you to listening to this presentation, and I hope it gives you enough insight into the family of Khronos Compute APIs so you can find out more details about the standards that may best suit your requirements. Khronos is committed to provide a safe space for companies to cooperate to create open standards that benefit their own business and the wider industry, including embedded and safety-critical markets. Your company is encouraged to join Khronos for a voice and a vote in any of these standardization activities, especially if you plan to implement a Khronos standard on your silicon or use a Khronos standard in your application or system design. If you are a member of EMVA and don't wish to join Khronos right away, then please apply to join the Cameros advisory panel. Whichever way works for you and your company to get involved at Khronos, you will be very welcome. Thank you.